Hello, I'm Ron Miller, and welcome to the Drive to Knowledge podcast. Today we have with us Peter Holst. He's the CEO of a company called FPRIN LLC. Peter is a mechanical engineer, and over his 35 plus year career, he has engaged in over 200 different development efforts, mostly focused on medical device development and particularly focused on drug delivery devices. Peter is an expert in an engineering approach called KDPD, or knowledge-driven product development. In knowledge-driven product development, what you do is you focus on doing the upfront work to really understand your design. You would blend the analytical with the empirical to arrive at a design that is much more robust and much more scalable than manufacturing. So we'll start off. Peter, thanks for joining us. Can you just give our audience a little bit of introduction to you and your company, FPRIN?
Sure. Thanks, Ron, and thanks for joining us today. So I'm Peter Holst. I'm a mechanical engineer, and I've been practicing as an engineer for about 40 years. And for the last 15 or so, I've been very diligently performing this methodology of knowledge-driven product development that Ron has mentioned. But I realized that when I look back over my career, my very first job, I actually began applying this kind of thought process and didn't really even know what I was doing at the point in time. But it was my first job was in the semiconductor process equipment space, and one of my very first design tasks was to design an electrostatic wafer flattening cassette for direct fab using e-beam technology. And so I realized I didn't even know the first thing about what's important, what's not important, and so began to think a little bit more about what's really going on when I'm trying to flatten this wafer using electrostatics, and realized that what I was basically doing was building a parallel plate capacitor, and then just went in and cracked open my physics books and things like that, and looked at what were the basic governing terms and principles, parametric values that defined how much force we would realize from a construction from a system like this, and then also of course looked at, well, how much force do I really need to flatten a wafer, and so that really is an application of the thought process and the methodology. And
so you really were doing knowledge-driven product development from the very get-go in your career.
Before I even knew what the heck I was doing. Yeah.
Excellent. So when we talk about knowledge-driven product development, sometimes I think it's easier to start off when you're trying to describe what something is, to start off with an analogy or a comparison. You and I have discussed about Elon Musk describing kind of the opposite of a knowledge-driven product development approach or first principles approach to a design by analogy. Maybe if you could explain what a design by analogy is, and then contrast that with knowledge-driven product development, maybe we can get a better understanding of what exactly it is that a KDPD approach brings to the table and why it's of benefit.
Sure, and of course, I mean, we didn't invent these terms, but I think they're very apt and very applicable to what it is we're doing. But design by analogy is essentially looking for analogous designs in a different application, or perhaps a similar application. And the reasoning goes that, well, it worked there then, so why won't it work now? And what I think it short circuits or short changes is the idea that you don't really think through, well, what is it that made it work in the previous implementation, and why might it or might it not work in this implementation? And I mean, it's perfectly legitimate to reuse designs. And in fact, I think it's one of the maybe basic precepts of a design effort that you don't want to break new ground or push boundaries on everything. You want to basically leverage the things that are in existence that are applicable. But it does require that you think carefully. In order for this to do successfully, it requires you to think carefully about things like, well, why did it work then? Why will it work now? Are the circumstances the same? Are the constraints the same? Are the goals the same or similar enough that you can just simply sort of replicate the previous design elements in your new design?
Okay, so when you're talking about knowledge-driven product development, then you're really talking about starting out with asking a lot of why-based questions, right? So if getting to the first principles approach, can you just explain what the first principles? I know your company FPRIN is based off of that, the combination of those two words, first principles. Can you just describe what that means to you and how you use that in the engineering design process, and how you use that to come into a KDPD approach?
So knowledge product development amounts to is to try to understand or to base your design on knowledge, to base your design on data, on information, on understanding. And it starts, I like to think a lot about the V diagram approach and model and methodology. So you start with market requirements up at the top of the left side of the V, and from that you propagate down into product requirements, and then lower levels system requirements, down all the way down to component requirements. And then up the other side of the V, of course, you're verifying those requirements until you get back to the top where you have to do validation. But the point is that you think very carefully about what it is that what are the market needs, what are the product needs that serve those market needs, and then what are the subsystem or component needs that serve the product requirement needs. And the way to do this is to think carefully about how big does something have to be, how much energy do I need to store, how stiff does this thing need to be, how insulative does it need to be, how much pressure drop can I afford in a certain fluid delivery passageway, those sorts of things. Because all those things inform one another. And ultimately, when you think about a complex system, it's really, you can always break it down into a collection of less complex systems. And then you have to think about the interfaces and how these less complex systems and components serve the needs of the ultimate product requirement and market requirement. And these things are all amenable to mathematical modeling, and we don't always start off with very, very complex mathematical modeling. We most often start off with fairly simple mathematical models that we can write equations and sketches and things like that on paper or whiteboard. But these are the fundamental things that provide us with knowledge that allow us to execute the design in a way that will allow us to integrate and meet system level requirements.
So when you're starting off, you break everything down into the component level, the subsystem level. You look at what exactly is required at each of those levels in-depthly, right? And then when you gain that knowledge, then you translate that into mathematical models for all subsystems, or is it just a set of subsystems that you feel are more complicated? What's your thought process in terms of determining what gets modeled out and what doesn't need to get modeled out? Or do you model out everything?
Yeah, a good friend and colleague of mine says that the right answer is that the right answer for the meta-analysis is never zero. So you do at least a cursory analysis, to at least establish that this is something that's not going to be a risk element, that's not something where you need to be very concerned about certain aspects of the design, and is this a make or break kind of a thing. But by doing these sort of high-level analyses, you can at least establish which are the things that we need to dive more deeply into, and build out more detailed analytical models. But you learn something from even the simple models. It's by looking at these things in a model on a model basis that you begin to understand what are the things that are likely to be risk elements. What are the things that have primary drivers, have higher order power or cubed or quadratic dependencies, those sorts of things, fourth power dependencies, and then you begin to understand, well, what are the things that I need to be really worried about when I'm developing this particular design for this particular device.
I know we've talked about this in the past. When you first start off, it's usually pretty simple scoping models that don't take a long time to set up, right? It can give you a fairly in-depth knowledge of a particular component or subsystem. Can you describe that process and what types of information you can gain and how long it takes to get to the point where you're actually getting a deep understanding or a deeper understanding of your design, and then we'll talk a little bit later about how how those models progress and get more complicated.
Sure. For these first level models, these scoping models, it can be anywhere from a couple hours to a couple of weeks, depending on what it is that you're trying to understand. And one of the things that I think is most important about these models is that it teaches you what you don't know, and what things you cannot perhaps find in a materials database or a catalog from a supplier for motors or sensors or things like that. It teaches you what it is you need to establish by test. And so we don't profess to rely only on analytical modeling. We think that we get good information from both physical embodiments of systems or components, so test, as people traditionally think about it, or analytical modeling and test, because you really can test things either in a simulation environment or a physical environment. And both of those things provide useful data to help you understand the design and build out really what amounts in the end to is a suite of design tools, a suite of tools that help you to drive the design. It helps you to inform the design. So the design team has tools that they can use to understand what are the attributes that you need to implement in your design execution. So as
in your experience over your career, you've seen these simple scoping models that can take just a couple of hours to a couple of weeks, like you were saying. Once they're implemented, you drastically change the direction, gain knowledge that you wouldn't have gained any other way, and drastically change the direction of a project and save a lot of time and money, rather than having to go ahead and empirically find the answer, or I guess never find the answer, right? And just have the project.
Yeah, absolutely. I mean, I always think about the proverbial brick wall. Where does your design run into the brick wall? And by doing these things, it allows you to see that brick wall a lot further down the road, so to speak. Yeah. And we'll talk a little bit later, I think, about some of the other things you can do with these design tools, with these models. The whole concept of a digital twin is something that's really powerful and something that's employed in a lot of space, in a lot of environments, a lot of technologies, transportation safety, for example. So what you can do is you can learn things about the design direction that you're pursuing and whether it's likely to be one that's going to lead to a robust.
So just give me an example of you don't have to get into specifics because I know a lot of this is confidential, but just give me an example of a project that you engaged in where it was pretty fast. How long did it take and to get to a point where you were like, oh wow, we are really looking at the wrong thing. You need to be looking at this instead, and just took the project onto a different tangent. Without that use of the analytical approach, the scoping model, you wouldn't have seen that. Can you just give a brief example of that?
Sure. I mean, there are a lot that I can think of, but I'll draw on one, and it had to do with an electromechanical needle insertion system. And so in this case, the design team had built a fairly simple model early on, and from this they had drawn some conclusions that in fact were erroneous because they had made some poor assumptions about the nature of the load. This resulted in them sort of boxing themselves into a particular design configuration that really was much more limiting than it needed to be, and because of the nature of the load not being in this case substantially inertial, resulted in sort of opening up the design space and allowing consideration of different gear ratios and things like that have much different characteristics with respect to reflected inertia. And so it allowed the potential of a much more robust design that had larger margin and various other things that were.
Yeah, and I know we've talked about other projects that you worked on as well, where you were called in to help them understand, for instance, I think it was a seal. They were trying to design a seal that didn't need to be lubricated, and you came in and basically, with a few hours of scoping modeling, realized that there was no solution set that would allow you to do that. Thus, stopping spinning their wheels for a fairly significant period of time. And I think that's important, right? Because you're not just wasting man hours, you're also wasting opportunity cost.
Yeah, absolutely. And so I think design, as designers and engineers, we're hoping for a good outcome, and we say, well, maybe just one more to give me the results that I want, and I'm not getting good data here, but I'll just try one more time. But having the understanding that you're really not going down a path that's likely to ever be fruitful is obviously really powerful in terms of allowing you to direct your efforts in a way that's likely to lead to a successful outcome. The example you cited, Ron, was one where the interest was in not lubricating the O-ring, which is laudable. You don't want to add extra steps in manufacturing, particularly steps that are difficult to control and difficult to monitor, like applying lubricant. But in this case, the choice really came down to, you want a robust design solution, you have to lubricate the O-ring. And this became very obvious based on a simple exercise that was a matter of a couple of days at the most, I believe, and that provided the insight that said, okay, lubrication is the right way to go, and now you get to a robust configuration, and you also get information as to where you can operate in the design space of sort of O-ring compression and lubrication to meet, in this case, orthogonal goals. And it's a fact that very often engineering tasks are bounded. I mean, they're always bounded. They're always constrained problems. And very often the goals are orthogonal, and you need to meet the requirements of two things that are not aligned, essentially. And finding this space, this intersection, and that gives you a robust solution is difficult. But with a simple model, you often see that, where do you need to be working? And now you can begin to focus your testing in that area where you expect to find a robust solution. If we have data that tells us one thing and a model that tells us the other thing, and they don't agree, then we know that either the data are being collected, or we're measuring something in a way that's not representative, or the model is not right. But we strive for a scenario, a situation we strive to be in this place where we have model data and analytical data and empirical data that are essentially aligned.
Yeah, talk more about that. Talk more about how that process progresses. So you start off with simple. You break down the design into your components or subsystems, and then you start off with simple scoping models, and then those models can and do progress up to a full-on digital twin. So you can talk using the analytical and empirical along the way to help inform each other. But the ultimate goal is to have, if you so desire, a digital twin. Tell me about some of the things that you can do with that, either at the subsystem or full system level. I think that's pretty interesting, especially when it comes to the benefits you can get from moving into scaling, the ability to iterate virtually versus having to do it empirically.